Alright, so this is a quick review of inverse functions. Now, we all know what functions are. For example, f of x equals x squared. And we know that if we put x into a function, f of x, we get, y or some other kind of thing back. An inverse function essentially is what we consider the opposite of a function. So f minus 1x. And this is what happens if we put y in and we get x. In other words, if we put x into f of x, and then we put the result in f inverse of x, we automatically get x back. That's what f inverse means. Remember that f of x does something, f inverse of x undoes it. And more formally, what we say is f of f inverse is equal to x, and f inverse of f is equal to x. So that means the first one says if you put x into f inverse and then put the result in f, you get x back. And so that's like going the opposite way, because if f of x is undone by f inverse, then f inverse also f also undoes f inverse. You can go either way, even though we know in function compositions that's not always going to work. So let's look at an example. If I have f of x equals 5x minus 1, right? Okay. So let's just write this as y equals 5x minus 1. And remember that if for f inverse, you're essentially switching the places of x and y. Instead of having x as the input, y is the input, or what you consider the old y, I guess, is the input, because we want to use y for output. So it's kind of like confusing because you're kind of switching the letters around, but let's just do it because it's going to be much easier if we just write this down instead of me yapping about it. Okay, there we go. I just switched the letters around because that's the whole point, right? We're switching the rows of x and y. And so now what we're going to do is we're going to solve for y. So x plus 1 equals 5y, and then y is x plus 1 all over 5. And so this is essentially the opposite of the original f of x. And you can see that in the original one, you multiply by 5, then subtract 1. Here, it's also sort of the complete opposite. First, you add 1, and then you divide by 5. So it's kind of like you're doing it the other way. And just to check our work, let's see what happens if we do f of f inverse. That means we have 5x plus 1, and x, because the thing we're putting inside f, this thing over here, is f inverse of x. We're going to put the formula for f inverse of x in, and then you notice the 5's cancel out. We have x plus 1. Oops, that's a minus 1. That's why it didn't work. Minus 1. I need to write things down correctly. We get x back. That means f undoes what f inverse does, which makes sense because, as we just mentioned, you're doing the opposite things. You're subtracting, dividing, or you're adding and dividing in a different order. And I'll let you check f inverse of f is equal to x. It's like the same thing. So the other thing is, graphically, how do we, if we say like had a function, if we had the graph of a function like this one, so y equals f of x, with the x and y axes, how do we find a graph of f inverse? And it's actually really easy, because remember that you're switching the x and the y. So let me draw another picture. Instead of having x and y like this, you really want x to go over here and y to go over here. So you're essentially mirroring these two axes, and the thing that cuts between them is the line y equals x. Is the line with y intercepts 0 and slope 1 is a diagonal line. So what we can do is we just basically go, I want the inverse of this cool looking function up here. Well, let's just mirror it around y equals x. Let's just mirror it around the diagonal, and poof, you have a function, or you have the inverse function, which is totally cool. Practically, if it's on paper, it's just really easy to like either fold the paper or flip it backwards, because it's really hard to conceptualize this most of the time. But since it's on paper, you can just like fold it or flip it, and it'll be way easier. Two things about inverse functions. Two very important things about inverse functions. Number one, f inverse of x does not mean 1 over f of x. Now remember that when we have x to the minus 1 in exponent line, it means 1 over x. But when we do functions, f minus 1 on top doesn't mean exponent, it means inverse. There are very few functions where the reciprocal 1 over is the same as the inverse. It works pretty much none of the time, so don't do that. The second thing is, not every function has an inverse, or not every function is invertible all the time. And let me show you an example, a very simple example. Y equals x squared, right? That's a nice function. It's a parabola. Let's do this algebraically and geometrically. First of all, I want to find f inverse, I want to find y inverse. Let me just switch this. And so when I solve for y is square root of x. Now remember that there are two ways of thinking about it. First of all, a number has two square roots, right? And so where y is plus or minus square root of x, that's not a function. 1y gives you, or 1x gives you 2y's, right? Because you can take the positive or the negative square root. Y is positive or negative. Graphically, I have the parabola y equals x squared. If I flip it across y equals x, I get this thing, which is so totally not a function because it fails the vertical line test. In other words, I think some of you may already know this, this function fails the horizontal line test. If we switch the rows of variables going from vertical to horizontal in the original one, it's not a function. So that means that what we say is that this function is not invertible, because invertible means you have an inverse. Invertible, the ability to invert. So y equals x squared is not invertible. But, here's the fun part. If we just look at the positive half of the parabola and we invert it by reflecting it, we get a function. So y equals x squared with x greater than or equal to 0 is invertible. That means that if we actually restrict the domain, we kind of remove the part of the function that doesn't really give us the inverse, then we can actually invert part of it, right? It's not a perfect opposite, but it works half the time. That's better than working none of the time. So sometimes, especially with trigonometric functions, we have to do this and say, okay, we're only going to look at certain parts of the domain in order to be able to undo a certain function to find the inverse.